potential would start to decrease. And I told you you could measure the potential by using the Nernst equation. Okay, so we did that for just one substance actually. So I'll just quickly do it for a couple of other reactants. And just a second, let me open the board. So we'll do the same for a couple of other reactants. And remember, for concentration for this, how do you use the Nernst equation? That remember, concentration is a term that only applies to either solutions or gases. So whenever you hear the term concentration, that applies to solutions, aqueous solutions, or it applies to gases. So remember, for solids, the concentration is always taken as 1. So if you have a solid in the equation, its concentration is always going to be taken as 1. It's constant. So I'll just do a few more questions using the Nernst equation, trying to figure out what would happen to the potential. So here's another reaction, and in this reaction, there's an equilibrium reaction. I've got copper 2+, which is in equilibrium, gaining 2 electrons, and it's in equilibrium with copper. And the data booklet and the standard potential is given as 0.34 volts. I want to figure out what would happen if I decrease copper 2+ ions. Let's say the concentration of copper 2 ions, if it's 0.01 mole per dm cube. So if its concentration decreases, copper 2+ ions are obviously aqueous, and the copper over here is in solid state. Now using the Nernst equation, what was the Nernst equation? That the new potential is going to be, by looking at the equation, you would realize that you're decreasing the concentration of your reactant. So the equilibrium is going to shift in the backward direction, so that more electrons are produced and the potential should decrease. It should be lower. It should be lesser, it should decrease. So instead of 0.34, it should be a lower value. So I'm going to calculate that value. So the new potential is the old potential, E0, which is 0.34, plus 0.059, which is a constant, divided by Z, which is the number of electrons, which is 2. And it's the log of oxidized species. Oxidized species is the one that is on the left-hand side. So it's copper 2+, and its concentration is given as 0.01, divided by the log of the reduced species, which in this case is copper, which is a solid. And solids have a concentration of 1. So that would be taken as 1. It's going to be taken as a constant. And you're going to take the log for this. And it's not 0.3, it's actually 0.34. So remember the Nernst equation, it's E0 plus 0.059 divided by Z, log of oxidized over reduced. So that is what the Nernst equation is. And you're going to solve this. I think log of 0.01, log of 1, I think, is 0. And log of 0.01 is, I mean, this is actually 0.01. So this is, I think, 10 to the power minus 2. That's the value. So it's going to be 0.34. Can somebody try and calculate this, what the value is? 0.34 plus 0.059 divided by 2 into -2. So if you do that, the 2 gets cancelled out. So it's
0.28.
Kitna is 0. So you're getting 0.28 volts. So anyways, that's the Nernst equation. So remember, you just put in the values and you will get the new potential. So it is coming out to be lower. Previously it was 0.34, but now it's less than that. So remember the Nernst equation. Okay, Zahib, is this clear?
Yes, sir.
Okay, let me. So that's our Nernst equation. The next thing we're going to talk about is moving to another subtopic. And this one is about electrolysis. So we're left with electrolysis. Now, the same exact concept applies that when you talk about electrolysis are different from cells. Electrolysis is the decomposition of an electrolyte by the passing of a current. So it's the decomposition of an electrolyte by passing electricity. An electrolyte is anything that's going to gain or lose electrons. It's going to contain ions. It's a process where electrical energy gets converted to chemical energy, or the electricity derives or drives a chemical reaction. So it gets converted to chemical energy. Now that is what electrolysis stands for. Electrical energy gets converted to chemical energy. Now the difference between electrolysis and your normal electrochemical cell is that you've got a battery, you've got an EMF over here, and there are two electrodes that this battery would be connected to. These two electrodes, let's assume at the moment they're inert electrodes, which means they're probably made out of platinum. So at the moment, we're just assuming, okay, these are inert electrodes. Now you've done electrolysis in O-levels before. You're going to dip the two electrodes in a solution. And that solution is going to contain some form of electrolyte. So here's the difference. In electrolysis, the battery is the one that's in charge. The battery is the one that's sending electrons towards one side, and it's pulling electrons from the other side. There is reduction that's happening on the right side, and there is oxidation that's happening on the left side. I mean, the side doesn't really matter. There's reduction that's going to be happening at cathode. And there's going to be oxidation that would be happening at the anode. So the difference now is that the substance doesn't have a choice. Anything that comes at the cathode, it's got no choice. The only thing it has to do is it has to gain electrons. There's going to be reduction, there's going to be a gain of electrons. So you don't have a choice at cathode. Remember, previously reactions or electrochemical cells had a choice. Like previously, what was happening? If you go back and have a look at the electrochemical cells, when you had electrochemical cells, then it was the cell or the electrode that was deciding whether they were going to lose electrons or whether they were going to gain electrons. One was the higher potential, the other one was the lower potential. So it was all up to the reactions over here. One wanted to gain electrons, the other wanted to lose electrons. So there was a current that was flowing in the wire because of the chemical reaction taking place. So there was a net production of current or electricity. But now it's the exact opposite. Now the reactions are not the ones who are determining who's going to gain electrons, who's going to lose electrons. Now the difference is that you've got a battery which has an electromotive force, which has an EMF, And that EMF is driving these electrons. So if X comes over here, it's got no choice. It only has to, I mean, there is no other option. It has to gain electrons. And if there's another substance Y that reaches the other end, then it has no choice. The only thing it can do is it has to lose electrons, because the battery is going to take electrons away from it. So that's the difference. Electrical energy is getting converted into a chemical energy. So on this side, substances would have to gain electrons. They have to get reduced. On the other side, they would have to lose electrons, and they would always have to lose electrons and get oxidized. So according to what we have studied so far, who gains electrons? The higher one, the one that has a high E naught. That is the one that gains electrons. And who loses electron? Who likes to lose electrons? The one that has a lower E naught. So I'm going to do an example of an electrolysis first. So I'll just copy the same diagram over and over again. So let's just copy this, and I'm going to put in an electrolyte, an actual electrolyte. And we're going to do an electrolysis for that. So here's my electrolysis, and instead of the X and Y, my solution contains, let's say, NaCl aqueous. So this solution is NaCl, and it's aqueous. Just a second, wrong. So this solution over here, one second, so it's NaCl aqueous, and we'll do its electrolysis first. So in NaCl aqueous, the first thing you're going to identify is this side is the negative side. This is the cathode. And this other side is the positive side. That's your anode. So all the positive ions are going to get attracted to this side. So it's going to be Na+1. That would go over here, and there's going to be Cl-1 that's going to go to the other side. Now, the only difference in O-levels and A-levels is that in O-levels, you would write H+1 and OH-1 ions. But remember, these ions, they don't really exist. I mean, the quantity of H+1 and OH ions in water is negligible. So make sure you remember this. I'll add this as a point over here. That make sure you note this down. That water ionizes very weakly. I mean, basically, its ionization is almost negligible. Like water, if it ionizes, it's going to produce H+1 and OH-1 ions, and their concentration is almost going to be 1 × 10⁻⁷ mole per dm cube, which is almost negligible. Like you can ignore them. This other OH ion would also have the same concentration. So they're almost non-existent. So you're going to ignore H+1 and OH ions, as their quantity or their concentration is negligible. So unlike O-levels, don't write H+1 or OH ions. They are not to be written over here. Okay, so whenever your solution is aqueous, just remember there is no H+1 or OH ions. What there is instead is water molecules. Remember, water wasn't ionizing. So instead you have water molecules, and water molecules are neutral, so they're everywhere. They're on the right side, they're also on the left side as well. So they're present at both electrodes. Basically, they're everywhere. It's an aqueous solution, so water is going to be everywhere. So yahan tak, is this clear, this point? Clear? Maria, Hafza, Sam, is this clear?
Yes, sir.
So just make sure you remember this, that don't write H+1 or OH ions. Always write water. I mean, water most of the time is just water. There's hardly any H+1 or OH ions. And water is going to be at cathode and water is going to be at anode as well. Now, the next part is, let's focus on cathode. The question is, who's going to gain electrons? So the electrons are coming in. And there are two things present. There's Na+1 and there is H2O as well. Now, one out of the two has a higher tendency to gain electrons, and we're going to try and figure out which one. So what I need is, I need electrode reaction. I need to figure out whether Na+1 or whether water likes to gain electrons. So the one that has a high E0 has a greater tendency to gain electrons. So I'm going to open the data booklet. I'm going to try and find equations for them gaining electrons. So this one, just a second. That's over here. And I'm going to look for equations in the forward direction. Remember, what I'm going to do is, where's Na? Probably over here. So what I'm going to do is, I'm only interested in the equation. Remember, ignore the reversible sign. Forget that the reaction was ever reversible, because now you don't have a choice. Na+1, you've got Na+1, and the only thing it's capable of doing is it's going to gain electrons. So that's the only option. So I'm going to write it as it is. It's Na+1 plus 1 electron, and it would form Na. I'm not going to add a reversible sign, because the only option available at cathode is that it's got to gain electrons, and it is minus 2.71 volts. The other thing that we had, so I've written this over here, the Na+1 equation. Remember, I'm not adding any reversible sign because you don't have a choice. The only thing that they could do is they got to gain electrons. Now I'm going to look for equations with water is gaining electrons. So remember, it's only supposed to be water, nothing else with it. So we're going to search for equations. For example, over here, I've got an equation where water is gaining 4 electrons. But I'm not going to use that because it's not just water that's gaining electrons. You need oxygen as well in this reaction, which you don't have. So we want equations where water is gaining electrons. And if you look carefully, this is 1. Here's another equation where water is gaining electrons, 2 electrons. So I'm going to copy that. It's 2H2O plus 2 electrons. And the product is H2 plus 2OH minus 1. So the potential for this one is minus 0.83 volts. So let's go back. So I've written down both of these reactions. Okay, there is no reversible sign present. You got no choice, only forward reaction. So who gains electrons? The one that has the higher potential. And the higher potential in this case is minus 0.83. That's the one that has a high E0, and that's the one that's going to gain electrons. And that's your so Na+1 would not be the one over here. Na+1 would not be the one that would be gaining electrons. It's going to be water because it's got a greater tendency to actually gain electrons. So is this clear, this one? Clear or no? Zoha, is this clear, Zahib?